I drew a camera here just so I know what pin to talk about. All right. Okay, now what am I telling you? I'm telling you now, as we agreed, that I have this disconnector here closed. All right. And this one is closed. And the disconnector below is closed. And what about this feeder? It's working here, supplying your loads. Is that good? So this bus bar now has voltage on it, which is in what color? In this red color. And the bus bar above will have this voltage, which is in what color? In this blue color. Is that good? So of course the voltage reaches up to the terminals of the disconnector here. And the other voltage, which is in this red color, will reach up to the disconnector from the what side? From the other side. All right, he said. In this case, if you want to close this disconnector, what will you do? You must make these two voltages the same. How do you do that? He said, well, you must connect between the two parts, and then close the two parts together. So who is always capable of opening and closing the loads? It's the breaker. That's why I will use the bus coupler. Now connect the red voltage from here, and when I come to close this disconnector, it will connect the red voltage up to this point, right? Also, connect the voltage, which is in blue color, down to here. Close this disconnector, and it will connect the voltage here as well in blue color. If I come and perform synchronization by comparing the voltage of the VT of the bus coupler and the bus bar, and the circuit breaker is closed, what will happen? The two voltages will now be aligned with each other with the same voltage. Now the two voltages have become the same, so the voltage coming to you here, which is in yellow color, is now established. It goes around like this and goes here, then goes to the lower bar, loops through Q2, goes here, and reaches the terminals of Q1. So Q1 now has the same voltage before and after it, because the two bars have now become a single piece, having been closed together. The two bars are now aligned and they remain the same, having become the same wave, the same single wave. In this case, if you close Q1, you won't have any problem because there is no voltage difference across the terminals of your disconnector switch. All right? So in this case, what do we call it, engineers? We call it load transmit. Okay. In some stations, we find that the bus might be before the breaker. Is there a question? Let's assume that Q1 and Q2 are open. You can unmute and ask me if you didn't understand. I mean, they are open. This is the first scenario we talked about initially. Engineer, hear me, Bashan? Yes, I hear you. Go ahead. I mean, the one at the bus coupler. No, as I told you, we will close it. I mean, we will close Q11 and Q12, so I will go to the bus coupler and close the disconnectors and then come to close the breaker. It will have the same control circuit as the breaker, and it will check that the VT isolator and the VT MCB will perform the same action that will charge it for us. So, as I told you, I will do it, I will close it, but before the actual action, and there it also has interlocking just like mine. I will close the disconnector and close the disconnector, and then come to close the breaker. I will find the PCU checking synchronization or the control we talked about. It will check synchronization and ensure the PT reading, and it will close the breaker under synchronization. So this is all set. Okay? Okay? Engineer? Thank you. Thank you. All right, Engineer Zain. Well, sometimes we encounter, as I told you, something like this with the bus coupler. So what do you do then? He said, well, it's simple. I will do something very simple. I will close it, Engineer Zain. I will close Q21 and Q22, then close this breaker of the bus section under synchronization, and close this disconnector, and close this disconnector. And if I also have a breaker here, I will close it under synchronization as well. So I have closed the entire upper bus together and close the bus that below. All together, then I will close the distant one. So it's as if I took the voltage here from this bus coupler, passed it through the bus section, brought it down to the distant bus coupler, and returned it to the lower bus, and went here like this. So now I have made a coupling between the two buses. Just by closing the loop with the distant coupler. Is everything clear now, engineer? I think now the matters have become clear regarding the disconnector and what beautiful, nice before. Okay, what have we finished here? We finished the story regarding what? Regarding the knife switch. Oh, almost, yes. I had written a table here, but I also made it in a better way. All right, so don't worry. I'll just fix this paper for you and send it to you, okay? Okay, great. We'll be back here in a second. Of course, we have now finished the interlocking specific to the D627. So if you come here and look at the D627, you will find here it says key 631. And from it, a contact normal close is missing. We agreed that all the disconnectors, which are the disconnector air switches, are drawn in the drawing as if they are open. So all the contacts related to them are drawn with the disconnectors in the open position. So you have key 631, which refers to what? Key 631, here it is, should be open, and then it goes down here below. All right, here you have something called a bypass isolator, an interlock bypass, which is key 1 that I mentioned to you. If you activate key 1, it will bypass the entire story I told you about and directly provide. Or activate the contactor or the auxiliary that indicates the interlock is fine for you. All right, when it goes down, where does it go? To the panel here. This panel contains the earth switch, which is key 389. This earth switch is located on the bus bar, not associated with a specific cell, which is why its wiring is installed in a specific panel, right? Or should we stick with AD17? Make sure the bus bar is open, then go down and take key 633, which is open. Then there are 2 paths. The first path is if 629 is open and the breaker is also open. On the other side, if 629 is closed, of course, this contactor is normally open, meaning the switch itself is open, yeah? If the switch closes, it will close. If it closes, you will find it goes here to a panel specific to the bus coupler, which confirms something called the bus loop condition, meaning the nearby bus coupler is closed or the distant bus coupler. In the end, key 4A operates. What is key 4A? This is what we saw here in the circuit, which, if it operates, allows you to operate the disconnector. Is that clear? Great, my dear. Well, for the D689, it's exactly the same concept. But instead of checking the earth switch of the upper bus, you will check the earth switch of the lower bus. All right, great. Now, if I were to tell you, let's talk about the earth switch. The interlock of the earth switch is the easiest one. In the earth switch case 631 or case 633, both of them, the interlock of case 631 or case 633, these two are typically the same. They are typically the same as case 630 or case 633. Both of these are typically the same. The earth switch looks at what? It looks at the disconnector switches. So key 630 must ensure that the disconnector switch before and after it are open. The ones before it are D627 and D629, and the one after it is D630. Considering that the breaker is not an isolation point, this is 630, considering it is not a point. So you will find here D627, D629, D634, and the same applies to the other side. You might ask why they place the bypass isolator after a certain point and not above it. Why is it necessary, even if you are doing a bypass on the interlocking, to ensure a certain thing? I will tell you it's quite simple. First, D627 and K630 both have the same mechanism. So when it comes to bypass interlocking, the earth must already be open. Understand me? That's why when it comes to D627, to perform a bypass interlocking, you must ensure that D630 is already open. Otherwise, there would be a problem. Imagine you have this coming from the post with length and you performed a bypass interlocking, then what would happen? It would operate, right or wrong. And if K4A operates, it will allow you as if you are giving a command to the disclosure switch, and that's not logical. The ground must be open. Now, if it gives a command to the disclosure switch, will the disclosure switch close? No, it won't close. Why won't it close? Because if the ground is closed, the limit switch of LSA, which we even saw in the video, will actually be open. So K21 won't operate. But as a precaution, let's say what? No, it must operate. Now let's look at the two important things that differ. In the case of the transformer, as for the overhead line, there won't be any difference. They are very straightforward, or let's say very easy. Who are they? They are the disconnector switch, which is the line disconnector and the line earth switch. These are extremely important. So let's take it step by step. Regarding the line disconnector, we agreed that the disconnector looks at what? At the breaker and the grounds. So if I'm looking at the breaker, then my breaker, which is A6111, should be open, right? And is there another breaker? And are there other grounds, or what's the situation? Let's see together. He told you regarding the 600D and the 629D. The first thing, if he's checking on grounds, he told you what? Grounds before and after, right? Who are the grounds before? case 633 and case 631, assuming the breaker is not an isolation point. And who are the grounds after? Case 635. And there are grounds on the other side after the transformer, which is ES3, right? So you'll find it looks at case 631, look at case 631, then look at case 633 with you, and then look at case 631, then go down to ES3, which he told you is 13.810 kilovolts. Its earth switch should be open, okay? And case 635, which is the earth switch after that, should also be open. And the breaker A611 should be open, 13.10 kilovolts. Its earth switch should be open. Is that okay? And case 635, which is the earth switch after that, should also be open. And the breaker 611, what should it be? It should be open. You might ask, why not check if the breaker below is open? It's not an issue because even if the breaker is closed, the breaker here is open. So it's floating anyway. So it doesn't matter what's below. And anyway, the interlock we discussed yesterday requires that the breaker below must be open to close this breaker. So it doesn't matter. Okay, so this is easy, or this is easy because it is, or this is easy for you now. All right. Of course, if you weren't going to check anything more than this ground, and the breaker should be open. And if you are a person who knows how to work on, and your client allows you to perform any action you want, well, I have done this before at a station using, for example, the SEL411L relay or the MyCom P546, and I have done it before on the Red 670 and the REL 670, and I did it on the 77SD using the 87L communication through which I can fiber optic communication, which is the, as much as by the LLL, the remote signal, or what they call the inter-MyCom, for example, like in the MyCom relay, or the remote signal, as I mentioned to you, in Siemens, or in the SEL relay, for example, which is the communication bits. The important thing is that I can load some digital signals onto the fiber as I want. So I was doing interlocking between the two stations to check the grounding of the remote station and take the output contact from the protection array and put it in the interlocking circuit. But this is a bit excessive, meaning if the operator can see the stations together and can check something like this, then it's fine. And there's another way they actually do it, which is to close this off, how there can be coordination between the two stations. But I'm telling you, if you want to do it, it's not a problem. If you're just checking the grounds, just 1, 2, 3 are open and the breaker is open, just try to check the grounds below that are open. All right. Regarding the ground here, which is kit 635, what does the ground look at? It looks at the switches. Okay, the switch before it, 631, is open. 631 is open. All right. Is there a switch after it? Yes, there is a switch after it. It's not a wind, it's a breaker and ground. Didn't we agree that the breaker is at 13.8 kilovolts? The breaker on the other side doesn't have a disconnector switch because the breaker was originally small in size, right? So we said this breaker could be made withdrawable, meaning before the pull, right? Am I wrong? When I came to the high voltage, I found the breaker was large in size and I couldn't make it before the pull. What did I do? I installed an isolator or disconnector switch for it. So now the issue of being withdrawable has become a replacement for what? It replaces the disconnector switch. That's why if I want to close the ground, I must ensure that the breaker below is racked out. I must ensure that the breaker below is racked out so that I can close what? I can close my ground. All right, that's very good. So here, you will find that it tells you this is 630, which is the disconnector open. And you will find below here, the breaker or the breaker below is racked out. Okay? Here, this is serious talk, but let's add 2 more pieces of information. The switchgear, guys, always has something very nice. What is it? Now, for example, I want to close this disconnector above and the ground below is open. Well, if you are generally in the switchgear, you always find the interlocking. If any of you have worked, for example, in switchgear stations, you always find the earth switch on the switchgear side is operated manually, mechanically. All right, very good. So now, if you come and close this disconnector switch, what prevents you from going to the earth switch there, opening these shutters, installing the handle, and closing the earth switch? There's nothing stopping you, right? Am I wrong? That's why they do a slightly advanced move. What is it? For example, if any of you have worked with ABB, you will find something called an interlocking magnet, which they call RL2 or RL3. There are 3 RLs. I don't memorize them exactly. Anyway, there's an interlocking magnet. And the idea is that to open the shutter door, you press a push button so that this interlocking magnet operates and allows you to open the shutter door. Is that clear? So here, for example, there's another type that has what we call a knob, switch, which is like a lever that you move if you want to open the shutter door. You move it from the open position to make the shutter door open so you can enter, do your work, and then close it. To move it from one position to another, there's a lock in the middle. For this lock to work, you press a push button, and this lock is like a coin that pulls a lock you have, allowing you to move the lever. So when this lever moves, it means the door is open, and you can enter, do your work, and close it. Is that correct, or am I mistaken? So here with the 630, you can't just rely on the air switch being open. I must rely on the fact that this door switch, or the door of this section that I will enter and close, must itself be closed. So I need to ensure that the knob switch I'm talking about, or the relay coil I'm referring to in the ABB, or whatever it is, must not be in the open position, meaning this section is open. Then I can close the ground. So I need to be sure that it is closed. Now, with the 6113, it's not just that the air switch is open. The air switch is open. And also, what position should it be in? It must be in the position where the door or the section of the air switch is closed. In this case, when it comes down, I want to close the ground to bring the knob switch and put it in the position to open the section door. When I press the push motor, I will find that the interlocking magnet does not engage or work with me. Why? Because it will be taking interlocking from the upstream. And below, armor flow, this is closed. It won't allow me to open the section, preventing me from closing the ground. So you have 631, check here below that the ground is open and its knob switch is in the closed position. Plus, the breaker, of course, you might need to ensure that the breaker is open. Okay, as for the earth switch, we agreed that it is open. And what about the breaker here? The breaker is rack out. Well, the breaker can be rack out, but still, when the breaker is rack out, there is also a lock. I don't want to go into details at first because it varies from one manufacturer to another. There is a lock to prevent the breaker from being inserted again as rack in. I also take this into account with the interlock. The breaker must be rack out and locked, meaning it is secured as rack out. Therefore, once the earth switch is closed, if I try to insert the breaker as rack in, I will find the interlock preventing me from doing so. Why? Because the earth switch upstream is closed. Is that clear, guys? This is how my interlocking works. Now, someone might ask, what if, Engineer Rashad, I didn't have a transformer here, what should I do? Well, if you have a space here instead of the transformer and you want to close the ground, it's very dangerous if you close the ground and the line is energized, right? How do I know if the line is energized? By looking at the voltage readings, but I can't be sure just by looking at the voltage readings. So what should you do? Well, if you look at the part I'm going to point out to you now, this is actually an additional part in the drawing, and it's not currently implemented in the station. It should have been drawn or implemented, which is also a mistake by the working engineer. They should have drawn a bypass here, or there is a jumper on it. Actually, I prefer to connect a jumper on it because this part always appears typically in every drawing, but I actually put a jumper on it because it's unnecessary for me since it connects to a transformer. Okay, so what is this part, engineer? This part tells you how to know if the breaker on the other side or the breaker on the other side or all the things we are talking about are in a very simple situation. I look through the voltage transformer to see if the voltage is live or dead. But who told you that the voltage transformer is working properly? Isn't it possible that the feed isolator is open? Isn't it possible that the feed MCB in the box above is open? Isn't it possible that the feed MCB in the LCC is open? You told me yes, so I need to check all of these, right? You told me, right? So you will find here KV1, KV2, KV3. These are the three that we saw in the case of the circuit breaker you are looking at. Okay, and you will find here 3 normally closed contacts from 3 auxiliary layers. What are these 3, engineer? Come, let me show you these 3. If we go here, engineers, in the voltage transformer circuit, where is it? Here it is. In the voltage transformer circuit, we find in the circuit, it takes the red, yellow, and blue. The red, yellow, blue, and neutral operate the red with the neutral on an auxiliary relay, the yellow with the neutral on an auxiliary relay, and the blue with the neutral on an auxiliary relay. 3. Auxiliary relays operating with AC voltage. We apply to the auxiliary. These are 3 auxiliary relays that operate with AC voltage, not DC, AC voltage. These 3 are now connected to the VT voltage. So now, if this VT is actually reading a real voltage, then these 3 auxiliary relays should be energized. And if these 3 are energized, what will happen? If these 3 are energized, you will find here that their 3 contacts are open, which will not allow the earth switch to close. But if there is no voltage, these 3 will drop off and their contacts will return to close, as you can see, allowing the earth switch to close. So how do I know if a line is actually under voltage? For example, well, these 3 auxiliary relays are special auxiliary relays, meaning their drop-off voltage is very low. It reaches 15 or 10 volts as a secondary voltage to ensure that this voltage is indeed very low, almost like a dead voltage. If there is voltage in the middle, there will be a problem. You might say, isn't this a signal? Doesn't this cause operational issues? On the contrary, it causes many problems. Why? Because sometimes the lines, as you know, when you see them, for example, on the road while traveling in any country from Cairo to Alexandria, from Riyadh to Dammam, from Dubai to anywhere, the whole idea is that you find that there are 2 lines, which we call running parallel to each other. So there is always, even if you have a dead line, it gets affected by the line next to it. If you're talking about a 22 kilovolt line, I want to tell you it can reach 70, 80 kilovolts on the other line. So this induced voltage can essentially keep the oxygen lace working without dropping off, which of course becomes a problem for us. Anyway, as I was saying, this is basically the method they use in order to determine whether there is voltage on the line or not. All right, engineer, as I mentioned earlier, the idea is clear and nice. So now we've ultimately finished the interloop circuit.